Okay, so this time we're going to look at something a bit more complicated. We're still going to keep with conservation of energy, because while things can get somewhat complicated with them, as long as you approach it the same way on each of them, no matter how complicated it gets, it's actually pretty simple. So I've got a situation where I've got a spring, and I'm going to put a small marble. Is it a marble? No, that's actually way too heavy for a marble. So I'm going to take some object, and I'm going to put it on there. And I'm going to push this spring down, where this is the natural length of the spring. And the amount that I'm squishing it down is 10 centimeters. Okay? So I take an object, I put it on a spring, I squish it down a little bit, and then I'm going to take my hand off, and the spring is going to launch that guy up. Okay? I want to know two things. One, at a position when the spring is at its natural length and the object is beginning to fly off of the spring, what is my velocity at this point? And then finally, when it goes up, what's the highest point my final height there? How high does it go up? Okay. So, we've got a situation in which we're going to look for multiple things. Of the things that I will tell you that our mass of our object equals 0.3 kilograms. The spring constant of our spring equals, where do I have that written down? 500 Newton per meter. And I already told you that my compression is 10 centimeters. Okay, so what I'm going to do is I'm going to go through and I'm going to mark these points in ways that I can keep track of for energy. We haven't used blue yet, so I'm going to say that this is my initial energy. This is a second energy that I have, and this is a third energy. Okay, so I've got energy at 3 different points. Now, we've got a spring in there, we've got gravity, and we've got the thing moving. So we're probably going to need potential energy of a spring, potential energy due to gravity, and kinetic energy. We're going to ignore air resistance, like usual, and any friction or anything like that. We're going to say that this is an ideal spring. Okay. So what I'm going to do is I'm going to start looking at my energy at each point. Most likely I'm going to have potential energy from a spring plus potential energy from gravity plus some kinetic energy. Okay? So let's start off and look at our initial position. I've got a situation where let's make this height, this compressed height here, y equals 0 meters. And then up here is going to be probably y2. This is going to be y1. All right. So my initial energy is going to be, my potential energy in the spring is 1/2 kx squared, where x is our compression, plus our potential energy due to gravity, which is mgy. In this case, we're going to do y0, plus our kinetic energy, which is 1/2 mv0 squared. Okay, so we had a bit of technical difficulty there, but picking up more or less where we left off. I've got the situation where I've got 3 different locations, an initial position here, 0, 1, and 2. Okay, so initially I have 1/2 kx squared for my spring potential energy, mg y0, which is my initial gravitational potential energy, and my initial kinetic energy. Now, taking a look at this, when we've got it compressed here, my initial velocity, v0, equals 0 meters per second, because it's not moving until I let go of it, and actually starts moving up from the spring. So that goes to 0. And the way I've set up my coordinate system, this is y0. So that goes to 0 as well. My initial energy equals 1/2 kx squared, which equals 1/2 500 Newton per meter times x squared, which is 0.1 meters squared. Okay, so that gives me a total initial energy. And a total energy in my system of, where did I put that? 2.5 joules. Alright, so now I know the total energy that I have in my system. I've set up my coordinate system to make my numbers pretty easy on the first one, so I could find it pretty easily. Y equals 0 at that point, and our initial velocity is 0 because it's right as I'm letting go of the block. So we know at any given point, because of conservation of energy, we start with 2.5 joules. That means we end with it, and we have the same amount in between there. So if I take a look at energy at point 1, I'll have some potential energy due to the spring, plus my potential energy due to gravity, plus 1/2 mv1 squared, my kinetic energy. So filling these in, I'll have 1/2 kx squared, x1, plus my potential energy, mgy1, plus 1/2 mv1 squared. Okay, well, at this location here, 1, we've got the spring basically going back up to its natural length, which is right here. So, we have no compression on the spring, which means our x is actually equal to 0. So that guy is going to be equal to 0. I've got a situation where mgy1, that's 10 centimeters, plus 1/2 mv1 squared. I can plug in the other numbers here, but what I'm going to do now is I know that my energy at this point is equal to my total energy, 2.5 joules. So I've got 2.5 joules equals mass, which is 0.3 kilograms, times gravity, acceleration due to gravity, 9.81 meters per second squared, times 0.1 meters, my height at that position, plus 1/2, 0.3 kilograms, times v1 squared. Alright, if I evaluate these guys, 0.1 times 0.3 times 9.81 equals, this becomes 0.2943 joules, oh, not equals, plus 1/2, 0.3 kilograms v1 squared, 2.5 joules over here. So I'm going to take 2.5 minus that value. I'm going to subtract this off. Do the same thing to both sides. That leaves me with 2.2, oops, 1 joules equals 1/2, 0.3 kilograms times v1 squared. I'm going to multiply by 2 and divide by 0.3 kilograms. So I can get rid of that, get rid of my 1/2. 2, 0.3 kilograms. And that's going to give me 14.7. Joule per kilogram is meters squared per second squared equals velocity 1 squared. Well, that's good. So I'm going to take the square root of both sides, and I end up with 3.83 meters per second equals V1. So, all I've done to find my first of my values, this kind of runs along quite a ways, but to find my velocity, V1, because this is the velocity at the point 1. All I did was I took my total energy, which I found from this area over here, I found it to be 2.5 joules in the system. And then I set that equal to my total energy at point number 1. Some of it might be in the spring, but the way we've set up our system actually, there's no compression in the spring, so there's no potential energy there. It makes the math a little easier on us. There's gravitational potential energy, just a little bit though, because we're only 10 centimeters. Okay? And then we've got 1/2 mv squared, our kinetic energy. So this is one of the points where our kinetic energy is about the highest. It may not actually be completely the highest. So finally, let's take a look at our last location, E2. That's with the block up in the air as high as it goes. Some final value y3, or I'm sorry, y2 that we want to find. Okay, well when we look at that, our energy here is going to be equal to, we've got potential energy of the spring plus potential energy due to gravity plus kinetic energy. I should be marking these there at each of this final location. So I plug that in, E2, I'm going to replace this. Well, my spring, 1/2 kx2 squared, but it's not touching the spring, and also the compression is back down to 0 on that, so that guy goes away, plus mgy2 plus, well, what's my kinetic energy? When I get to the top, the highest point that it goes up to, like when I throw this up in the air, back up here, its velocity came to 0, and then it started on its way back down. So, our highest point is found when our velocity equals 0 meters per second. Because if we had a positive velocity, that means it'd still be going up, so it could go a bit higher. Or if it had a negative velocity, that means it's already on its way down, so it was higher. So the highest point, our apex, is defined by our velocity equals 0. So 1/2 mv2 squared, but our velocity is equal to 0, so that goes away. Well, this one's another one of the pretty easy ones. Energy 2 equals mgy2. Okay, well, our energy, our total energy, is equal to 2.5 joules, because that was our total energy in the system. So I know that this is 2.5 joules equals our mass, which is 0.3 kilograms times 9.81 meters per second squared times y2. So I divide by 0.3 kilograms and 9.81 meters per second squared. Do the same thing over here, 0.3, 9.81 meters per second squared, and the kilograms there, and I'm left with just meters. So when I evaluate this, let's see what I get. 2.5 divided by 0.3 divided by 9.81. I end up with 0.85 meters equals y2. So it goes up 85 centimeters. Okay, and I could go back in, I could find out how fast it's going when it's hitting the ground, although from the energy balance, or not the ground, yeah. So when it gets back down towards the spring, I could find out that it's probably going 3.83 meters per second. It falls right back down onto the spring, and then in the end it will compress the spring back 10 centimeters. So we compressed it, it's going to go up. Right here it's got some velocity, goes all the way up to here, and then it's just going to fall back down and kind of do the reverse. As long as we don't have any dissipative forces, non-conservative forces that take energy out of the system, it'll keep doing that back and forth pretty much forever. In real life, however, we have things like friction and air resistance that remove energy from the system. But this is a bit more complicated problem. You can see that we can get a lot of information from energy. We can find out what's happening in a bunch of different places where it looks like it'll be very complicated, but all we have to do is find our energy and then apply that to each point.